We're going to do our Unit 8 test review today. How I created this review, this is just information, okay? So it's important information that you need to know, definitions, steps for how to solve certain problems, stuff like that. I like writing it all in one document from my notebook so that I can have just one document that I need to reference rather than having a whole notebook of notes, okay? So it might feel repetitive, but we're just gonna go over things. As far as actual practice problems that you should do once we're done with this and after class, there are two extra practices in Canvas under the Unit 8 extra practice. There's one for 8.1 through 8.4. It's insanely long, okay? I'm not saying you have to do all of it, okay? It's really long. Pick and choose what you need. And then the key is uploaded for that one. I was up here till like 5 o'clock last night doing it. And then there's also one for 8.5 and 8.6. I have not made a key for that one yet. There are answers because I made it through my software, but there's no work. So that one is TBD.
Use software including ChatGPT.
Okay.
Oh,
What?
wow.
Software.
Oh, no, I have math software. Oh. It's called CUDA Math, and it like makes different worksheets for me. Yes, that's the key. Okay. All right. So we're going to start with 8.1, which was just prereqs. What? Prereqs. Prereqs meaning it was all old news. Okay. Nothing new here. So some things that we need to know. Okay. We need to know our exponent rules. Yep, we need to know our exponent rules. We also need to know our perfect squares, cubes, yes, fourths, and fifths. So there is a little table on 8.1 notes that has all the perfect squares, cubes, fourths, and fifths that you need to know. Yes, you could just do the math on your test. However, that is valuable test time that you do not want to be using doing that, because then you'll run into where you're running out of time because you've been multiplying 5 times, you know? So just having it memorized is much more helpful. So those are like the need to know things that you just have to like rote memorization. You just have to memorize it, okay? The next thing that we talked about in 8.1 was rational exponents. Rational exponents were just exponents that had fractions. Okay, exponents that had fractions. And for these, remember we always wrote them as power over root. Power over root. And so if it was in radical form, it would be like the root is here. And then the power is in the exponent. And if we wrote it in exponential form, it would be, so like there was an x in there. If we wrote it in exponential form, it would be like x to the power over root power. Okay. Okay, the next thing we talked about, really the last thing we talked about in 8.1 was solving rational. What? P over R, yep. Yep. Yes, they do. Solving rational equations. So these were equations that were like, I don't know, 4x plus 3 to the 2/3 power equals 7. Something like that. That's like an example. I just made that up out of thin air. Okay? But there were specific steps to how to solve these. Okay, so our steps were, we would isolate the exponent and variable. So isolate, no, variable and exponent. So what this means is like if there was a 3 out in front, I would get rid of that, okay? Now, once I have just the parentheses with the radical, I am isolated technically. So really we're isolating the parentheses and the exponent. Parentheses and exponent. Then we would raise both sides to the reciprocal power. Is that what you said? So if I had this 4x plus 3 to the 2/3, I'm basically raising it to the 3/2 and then raising this to the 3/2.
Actually, I might have accidentally said radical, not my argument.
It's okay. I mix those words up as well. And so what that does is it cancels the exponents over here so that I just have 4x plus 3. And then I have x to the 7/3 power. Okay, now what we need to do is we need to basically like convert to radical and solve. So this isn't the best example because 7 isn't great, but this is power over root. So this would equal a cubed root 7 squared. And it would be like 4x plus 3.
Yeah, I think 7's great.
Honestly, 8 would be better because 8 is a perfect cube. Oh, I get it. Sorry, that took me a minute. But you would evaluate whatever that radical is and then just solve like normal. Okay? Now, the only thing that was kind of tricky here was if there is more than one x, we have to check our solutions.
That took you a while to get.
Hmm?
That took you a while. 2.
Yep, so 8.2 is graphing exponential and log functions. So once again, we're going to do the same kind of thing. We're going to write down the important stuff. Okay, so I'm going to start with exponential. Okay, the parent function for exponential was y equals b to the x power, where b was the base. And the base had to be greater than 0. Okay, it was not allowed to be 0, and it was not allowed to be negative. Our exponential graphs looked, we're going to kind of draw, sketch one. So they had horizontal asymptotes.
I also not really good at this, actually.
The horizontal asymptotes were at y equals 0. So if I was to draw one on my graph, it would be like right here at y equals 0.
Exponential.
If you want to just listen, you can.
That's what I'm doing. Huh?
If you want to just listen, you can. It's totally up to you.
No, this is fun. I'm making it look like okay right now.
Okay, got it. All right. In the domain, we talked about the domain and range briefly. So the domain for exponentials was all real numbers, so it was negative infinity to positive infinity. And the range was 0 to positive infinity. We were not allowed to have negative numbers in the range, so y values. And we actually had a table that we could use for this. I'm actually going to make mine horizontal here. Are we okay with that?
No.
Actually, I don't think I like it.
I hate that.
Yeah. Let me scroll up. So there was a pattern for all exponential functions, okay? A pattern for how the x's and y's made their points. So the pattern was always -1, comma 1 over b, and b is the base. So -1 for the x, 1 over b for the y. The second point was always 0, 1. Always this.
And then wasn't the other one 1 over?
And then the last one was 1, comma b. And so our graph would look something like -1b 0, 1. It would look something like this, and it would never cross that horizontal asymptote. The only other thing I want to talk about with exponential functions is sometimes the base was a fraction. So when the base is a fraction, so if I had like 1/2 to the x power, we make it a negative exponent. So we would change that to 2 to the negative x power. For your test, you should be able to make a table. For any parent function. Still on 8.2, we're going to talk about the natural base.
Are we gonna do practice problems for these?
Probably not.
Okay.
It's on the practice, but I'm not going to do them in class.
Okay, wait, there are 2 practices.
So the natural base is represented by the letter E, which is approximately what as a decimal?
2.7.
2.7 what? 18. 2.718. So that's the number we use when we're talking about E. So if we have an equation that's using the natural base, it would be y equals e to the x power. And remember, this is still an exponential function. We graph it the same way. It just utilizes a special number because it's a special situation where it's exponentially growing. Okay? So when we do our table for this, we would have -1, 1 over 2.718. We would have 0, 1, and 1, 2.718. Okay? This is basically 1/2.
Basically, but if you write that on the test.
Don't write it on the test. Don't write 1/2 on the test. However, and then honestly, I should have my 1/8.
Wouldn't it
1/8.
Technically.
Technically. So when you're graphing it, anywhere between 1/2 and 1/3 is fine. Like, I'm not going to be a full-blown stickler trying to see, like, if your 1/2 or 1 over 2.718 looks like I'm not spending my time on that. Okay? So when you're graphing, just think basically 1/2. Okay?
Isn't it closer to 1/3?
It is closer to 1/3. If you would like to think basically 1/3, you can.
Okay. Just like brain. Why'd you do the little squiggle sign?
Because it's approximate.
Oh,
It keeps going on forever and ever.
Because we would do that for pi too, and this is practically.
Yep, it's practically pi. It's the same thing, just a different number. Okay? So that was pretty much the end of exponential, and then we started talking about inverse functions. Because I wanted to have more room to write this. So inverse functions basically meant that x and y values switch places. X and y values switch places. And the reason why we talked about this is because exponential and log functions are inverses. Yep.
Fun fact.
Hmm.
This morning.
So 7 asked why is just an x up here? Like, what does that mean? And so remember, we would then do like y equals, we could say like e to the negative x plus 2 and then minus 3. So that would mean we're going left 2, we're reflecting, and then we're going like down 3, all of that kind of stuff. Last thing to talk about with with inverses is that the inverse function, so we did one graph in 8.2 where we graphed the exponential and the log functions on the same coordinate plane. and they were reflected over the line y equals x. So it would be like, neat. Here's y equals x, okay? And so we had our exponential function that was like here. And then we had our log function that was like here. And so they were reflected over that. They were mirror images. All right, the last thing from 8.2 was log functions. So we're going to talk through log functions just like we talked through exponential functions. So the parent function for logs is y equals log, log base b of x. Okay, and then we also had another option, or y equals ln of x. And what was the base for ln? E. So that's like your E version for logs, okay? Logs, instead of having a horizontal asymptote, they had a vertical asymptote. And so that vertical asymptote was at x equals 0. And the domain and range switched places. So the domain is 0, infinity. The range is negative infinity, positive infinity. So meaning that our x values cannot be negative. And so remember, this is the reason why we can't put negatives into logs. We cannot take the log of a negative number because of that domain. And then our range is anything. And so we will also sketch a graph for this one. I'm really what? We did have parent function points for this one. So we had x, y, and it was switched from exponential. So exponential was -1, b. This one is 1 over b, -1. Exponential was 0, 1. Log is 1, 0. Exponential was 1, b. Log is b, 1. So they just switch places.
For which one?
What do you mean for which one?
What would it look like if they switch places at these numbers?
Like they switch places.
How's the equation supposed to look?
It's a log equation versus an exponential equation. Yeah. Next class.
What?
That's why we're reviewing. So our horizontal or our vertical asymptote is at x equals 0. And for logs, it looks more like this guy. All right, 8.3 was all about logs and their properties. So 8.3 introduced going back and forth between exponent and log to exponent, and then also two properties, and then we talk about the rest of them in 8.4. So remember, our parent function for logs is y equals b. Oh, no. Our parent function for logs is y equals log base b of x. And they are inverses with exponential. So the exponential is inverse to logs, meaning they go back and forth. Yes. Meaning they go back and forth. So I can go from exponent to log to exponent. You need to know, you need to be confident. Confident in going between the forms.
I wasn't feel confident about that.
Good. You need to be very confident. So exponential form, we use the abbreviation BEA, meaning base, exponent, answer. And so it was always base, exponent equals answer. And then for logs, we used LaBe.
LaBe and Bia.
LaBe and Bia and LaBe.
Bia and LaBe.
Bia and LaBe. So LaBe was log, base, Answer equals exponent.
Wow,
in
you
really
wrote
little
that
time.
really fast. I am not kidding.
Like,
To
I
be
put-
fair, I'm just copying, so.
well, so
I mean, so are you, I guess. But
on a technicality.
I'm really good at taking notes, so, you know. So we need to be able to go back and forth from exponent to log, log to exponent very quickly, very efficiently, okay? And there is tons of practice in that extra practice on going back and forth between the two, okay? Yeah, there is. And then the only other things we need to talk about before the properties is that we have a common log. So the common log has a base of what?
10.
It has a base of 10. And so if we have something that just says log of x, we need to know that it's base 10, okay? We do not write the base of 10. We just write log. We do not have to do the special thing in the calculator for log base 10 for a common log. We can just use the log button, okay? So there was the common log, and then there was also the natural log. The natural log was log base what? E. And how did we write that? Ln of x. Okay? You are not allowed to write these any other way than this. So they have to be written like this.
Wow, this is really going really fast here.
So like if we put a 10, we take points off.
I would. If you put a
You
10,
are-
I would take points off. If you put log base E instead of Ln, I would take points off. Not a lot of points, but still points. Okay, next we talked about some log properties. We talked about 2 different ones. Well, technically we talked about 3, but we're going to be big boys and girls and we're going to combine them to 2. Okay? So the first log property number 1, was if I had log base B of 1, it always equaled 0. So no matter what the base was, if I had a big 1, it always equaled 0. So that's how I remember this. Because I have little phrases in my head that help me remember things. So big 1 always equals 0. So there were a couple of those on your quiz. They should have been like 5-second problems. Big 1, 0. Big 1, 0.
Oh, I got those right.
Okay. The second property, that was technically 2 properties on the notes, but I think it can just be 1, was log base B of big B to the x power equals x. So if my base and my big number are the same, my exponent's my answer. Okay. This was separated on your notes to have 1 for with an exponent of 1 and 1 for with an exponent of x. But if there's no exponent with a number, what is that exponent? Like if it's an invisible exponent, it's 1. So it works either way. So like if I had log base 5 of 5, it would equal 1 because the exponent with 5 is 1, right? It's just not shown. So that was like a totally separate property in the notes. But it's the same as if it was log base 5 of 5 squared, it'd be 2.
Technically it's the same, it's just.
It's the same.
a little harder,
Yes. So it's the same property. So how I remember this is if the base and big number are the same. I know.
Sorry, that was.
Answer is exponent. This is just how I remember things. So maybe if it works for you, then it'll help.
No, it
Which I know it doesn't for everyone, but like I just have these little phrases. I just have these little phrases like Bia and LeBay, and big 1 always equals 0, and base and big number are the same, so the answer is the exponent. Like that's just how I remember things. Sometimes we couldn't use a property. So when we can't use a property,
Miss Adams, there's a glare. I can't see it. Can you please tell me what it says?
where
Big numbers.
big 1 always equals 0,
No, the next one.
big base and big number are the same, answer is exponent.
Hard.
Same, answer is exponent. So when we can't use a property, we solve. And so there are steps for solving. Okay, step 1 is to set the log equal to x. Set the log equal to x. Then we rewrite in exponential form. Rewrite in exponential form. Make a common base. Set the exponents equal.
I'm trying so hard.
It's okay. And then solve for x. So let's talk about this like we can't do it. So like if I have on your quiz, there was one question that was log base 27 of 9. I cannot use either of my properties for that problem, okay? Because I can't make the base 9 to a base of 27. So my steps are that I set the log equal to x. And then I change it to exponent form. So it would be 27 to the x power equals 9.
What?
This is what happens when we can't use a property. We set the log equal to x. We change to exponential form, which once again, we should be very confident in doing. Okay? And then the base that I pick is a base that both numbers can go down to. So both numbers can go down to 3. This x doesn't go anywhere. It stays in the exponent.
Is that supposed to say a 0?
No.
Oh, wait, just kidding. Sorry.
3 what gives me 27?
3.
3 cubed gives me 27. And 3 what gives me 9? 3 squared. So now I have the same base. So I set my exponents equal to each other and I solve. Okay, 8.4 is over the log properties. So this was a super short lesson. All we did was go from expanded form to condensed form. Expanded to condensed form. And remember, we could go back and forth.
Why is this 3 pages already?
I'm at 7 pages.
Same.
Oh, I think I just
Mine's horizontal though. Whoa, nice.
Wait, didn't we just do the log properties?
Did someone have to go to the bathroom?
These are the log properties for expanded and condensed. Okay, so expanded form was when I had something like log of m plus log of n. Now, if it has no base, what is the base?
10.
10, okay? And so that's expanded form. If it's addition, what would a condensed form be doing?
It would be log mn.
Good, it would be multiplying. So it's log of m times n. Okay. The second property is expanded. It's expanded for subtraction. So if it's subtraction, what am I going to do? Divide. Log of m divided by n. And it's always top divided by bottom. Or first divided by last. And then the last one is in expanded form. We have a coefficient, k log m. But in condensed form, it can go to where? Where would it go? Jail in the what? In the exponent? Yes, jail in the exponent. Another thing we can talk about is if we want, in condensed form, we have roots, has roots. So if I had something that was like log of x to the 1/2 power, in fully condensed form, I would write that as log square root x. That's something that I saw on the quiz. If it was 1/3, what would it be? Would it be a square root?
No.
No, it'd be a,
Negative exponent.
no. If it was 1/3 instead of 1/2, it wouldn't be a square root, it would be a cubed root. Good.
Wait.
All right, so 8.5 was solving exponential equations. 8.6 was solving log equations. So we did one lesson for one and one lesson for the other.
Practically the same because the log goes into exponential.
It's back and forth, yes. So for exponent, we go to log form. For log form, we go to exponent form kind of thing. There were two different methods here. If you want to go and write down the rules, you can. But basically, for method 1, it was like if we could make the bases the same, then we would do that and set the exponents equal to each other and solve just like we did in 8.3. And then if we couldn't make common bases, we would change to log form and then solve for x. So I'm going to focus on that one more. So method 1 was the same method from 8.3. If we had a fraction anywhere, we would turn them into change to negative exponents to get rid of the fraction. Okay, so fractions change to negative exponents. We did not do anything else with that.
Sorry, I need to stop.
Method 2 was basically if method 1 didn't work. So if we can't make a common base,
I'm playing myself.
so like when I had bases of 27 and 9, I could make the bases 3, right? Following? When I had bases of 8 and 16, I could make the bases 2. Yeah? So when I can't do that is when I go on to method 2. When I can't make common bases, I go to method 2, which is where I isolate the exponents. I'm going to say actually the base. Isolate the base with its exponent. And then we change to log form. We solve for x, and we will use the calculator. We did have steps for putting it in the calculator, so you have to remember how to put the log in the calculator when it's not log base 10. So if it's log base 10, you just use the log button, which is right next to the number 7 on like the number pad. But if it's log base 3, then I have to go to math. And then I have to scroll down to option A, which is log base. And then you have to click enter. That's not how you spell enter.
This part I can do. I can't do.
Okay. If it was ln, if it was natural log, is there a special button for natural log?
Yes.
Yes. So, or we would use the ln button.
Hold on.
So we would either go to math, option A, enter to do log base anything, or if it was natural log, we would just use the natural log button. The thing that's important you need to remember for your test is that you must show your work before the calculator.
Hate, but hate. No hate, but hate. Oh, wait, that was good actually. That was nice to know. How are you supposed to work?
You have to show your algebraic steps before you can just put things in the calculator. I need to see your work. So solving log equations, we actually did pretty well with this, I think. So solving log equations, basically solving log equations when we can't use a property, we have steps. So we have to isolate to a single log. And sometimes we would have to condense to do this. Then we would change to exponential form.
Oh my god.
And then we would solve for x and check for extraneous solutions. And remember, with this particular lesson, we were just checking for negatives. We can't put negative numbers into logs. Okay? So you're just checking to see, okay, if I take this number and I plug it into the parentheses for the log, will I end up putting a negative log in the calculator? Like a log of negative something.
Wait, you can't put
Now, sometimes if it's just log of x, if I get any negative solution, it's not going to work, right? But if it's log of x plus 7, okay, if it's log of x plus 7, but I get an answer that's x equals -3. When I plug -3 into x, I end up getting log of 4, which is positive. So that actually means that's good. Okay? So you truly do have to check and see. Anytime, if you have multiple logs in your original problem, if it doesn't work for one log, it doesn't work for anything. Okay? So if I have like a log x and I get a negative, then that's never going to work. Yeah? But I have to simplify what's in the parentheses with my substitution before I decide if it works or doesn't work. So the last couple more things with with 8.6. Remember, if I just have a log equals a log, I can drop the logs and solve. So if I have log base 5, actually let's just say if I have log of 10x plus 3 equals log of 17.
You cancel the x's.
Right, I can cancel the logs and I can do 10x plus 3 equals 17. But if I have log of 10x plus 3 equals 2 plus log 17, I cannot do the property for that one because of that -2. I can't drop the logs. Okay, I can't drop the logs there because of that +2. And then the last thing we talked about with 8.6 is doing log equations in the calculator with graphs. And so for these, we would put the left side in Y1, the right side in Y2, sketch a graph, and our answers are the intersection points. And so it would be like x equals blank, x equals blank. Okay, so it's just, our answers are the intersection points. So remember, we have to remember how to do like intersections in the calculator. So we would do like second, trace, 5, and then scroll, and then click enter 3 times. So you'll do second, trace 5 to get to the intersection, scroll close to the intersection, and then click enter, enter, enter. And then there was another layer to this where we did inequalities. Inequalities were the same thing. So we were sketching the same graph, finding the same intersection points as our solutions. We just had to know how to read the graph for greater than or less than, okay? So really this was a lot of interpreting the graph. Almost done.
Yeah, Miss Adams, you're really pushing my limits here.
Almost done. So we would interpret the graph, and if it was one piece was highlighted, we would just have like parentheses, parentheses, number, number, right? We wouldn't have any unions. If it was two pieces, then we would have like negative number to, or no, not negative number, negative infinity to number, union number to positive infinity if it was two pieces. Okay, so that was all just interpretation. So we would like graph something and we would have like one graph that looks like this and one graph that looks like this. And our answers are still our intersection points. So we would have x equals, but it was like, how do we use those x equals numbers? How do we use those numbers? And so we would like use our highlighters and we would say, okay, well, above would be here. So it's one piece versus below would be here and here. So it would be two pieces. And so using all of that to decipher was the last part. And that was the only challenging part of that, was deciding, do I write this as one piece or two pieces?
But yeah,